Hello everyone, I'm Hiếu Nguyễn from Hanoi University of Civil Engineering. Today I have honor to be here to present some interesting results concerning prediction of optimal cross-sectional area of Truss structure using artificial neural network. This is the outline of my presentation. First of all, I would like to introduce the reason and the purpose of our research. Secondly, I will present our proposed approach to solve the problem. In the third part, a case study illustrating the capacity of our proposed approach will be shown. Finally, I will point out some main findings of our research. So, in the field of civil engineering, the widely used method is the try and error method, in which two steps of sizing and checking are repeated many times until achieving the reasonable solution. Although this method is simple and easy to implement, there is no guarantee that the optimal solution can be found. The alternative design method is to use mathematical algorithm for searching optimal design. In recent decades, many meta-heuristic algorithms such as general algorithm, particle square optimization, differential evolution have been applied to solve structure optimization problem. As you can see in this slide, many optimization platforms have been developed based on mathematical algorithms. Besides the advantage, one disadvantage of the algorithm is that they cannot learn from historical data. For a slightly different design input, the optimization process still carry out from the scratch. If there exists an algorithm that can utilize the result obtained from the previous optimization, it can save a lot of time and human resources. In addition, in many design companies, after a long period of operation, hundreds of projects have been designed and a large number of design solutions are collected. This raises an issue of building a recommender system that can learn from the database and accurately predict for the new one. The recommender system will support designer by suggesting a good initial solution. It will speed up the design process and improve the quality of the design. Nowadays, the development of the machine learning provides an easy way to build such tool. As you can see in this slide, the above figure symbolizes the traditional design approach called the trial and error method. The below one is our proposal, which is called the data mining approach. In more detail, many choices of the same geometric layout, but various loading and design constraints are optimized using the differential evolution. The value of the applied load, the allowable sheet as well as allowable displacement are stored as input, while the optimized cross-sectional area of just member are collected as output of the training data. Then, a machine learning model will be trained by the training data. If the accuracy of the model is acceptable, it is ready to make a new prediction. The proposed method is illustrated through a numerical example obtained by planar Truss. This is a well-known problem that has been investigated in many previous work. The configuration of the Truss structure displayed in this slide. The purpose is to construct a machine learning model that receives design input, including the applied load, the street, as well as the displacement limitation, and returns the optimal cross-sectional area of 10 elements. For this purpose, the configuration of the truss as well as the material does not change, but the load and the design constraint vary to produce chaining sample. We have 11 values of the applied load, 8 values of the allowable stress, and 6 values of the allowable displacement. Thus, there are a total of 480 combination of the applied load and the design limitation. A combination is then used as design input of an optimization problem, and it will be shown independently using the differential evolution. In some case, it cannot find the optimal design. So finally, the database contains 271 samples present in this slide. The machine learning model used in this study is an artificial neural network. It's based on the biological neutral. On input are scaled with the corresponding weighted factor and sum up in the perceptron. The sum of the scale input are then transformed into the output by the activation function. The model used in this study contains many perceptrons that are organized in 5 layers. The input layer consists of 3 nodes corresponding to the applied load, the allowable stress, and the allowable displacement. 3 hidden layers contain 100 nodes per layer, and the output layer comprises 10 nodes, which are the optimal area of 10 members in this truss. In this work, the dataset is split into 5 parts, in which 4 parts are used to train model, while the last one is used to validate. The mean absolute error value during the training process is plotted in this figure. It can be seen that after 1000 epochs, the gap between the training and the validation loss is more and stable, indicating the conversion of the model. To check the accuracy of the model, it is used to estimate the optimal area of the truss with design input as follows. The applied load is 100 kV. The allowable stress is 25 KSI, and the displacement limitation is 2 in. This is the original problem that has been investigated in the literature. The predicted results as well as the true optimal area directly received from the differential evolution are present in the table. It can be observed that the predicted values are very close to the choose value, with the coefficient of determination equal 0.9999. It indicates that the developed model has capable to predict the optimal design with very high accuracy. Furthermore, the model is checked on the testing dataset contain 85 samples. It is noticed that the predictive model has never seen test sample before. This figure plots the true area obtained from the differential evolution and the predicted area obtained from the artificial neural network model. As you can see, the coefficient of determination is very close to 1. On red point located near the blue line represent the high accuracy of the predictive model. So this is some finding of our research. Our research present an alternative approach for optimizing church structure using machine learning. The developed model can quickly predict appropriate area of church member. It can save a lot of time and human resources. The developed model can be used as an effective recommender tool for engineers. So, thank you for your attention.